Okay, this is going to be my video lab report for Physics 2211 Lab 2 Falling Objects. The purpose of this lab is to observe the force of gravity via a real-life experiment, which is going to be a ball in free fall. And we're also going to compare that to two computer models, one of which only models gravity acting upon the ball, and the other one factors in air resistance. The outcome here is that the real-life experiment more closely resembles the drop of the computer simulation, which uses air resistance, because of course in real life there is air resistance. We're going to make some key assumptions for this lab. We're going to know that the camera records at 30 FPS, which means that every frame is 1/30th of a second. We're going to assume that tracker is properly calibrated to the ruler I used, which, as you can probably see later on, that is not the case. We're also going to assume that there is no force of anything other than air resistance and gravity acting upon the ball. And we're also going to assume at t equals 0, the gravity or the velocity of the ball is equal to 0 meters per second. There's some fundamental principles we need for this lab, the first of which is Newton's second law, which is F net equals change of momentum over change of time. We also need to know gravitational force, which for this lab we're just going to use 9.8 meters per second squared is equal to gravity. For the purposes of this lab, gravitational constant times big M little m over r squared is completely unnecessary because we're so close to the surface of the Earth, and the forces or the masses of these objects are just so small. We're going to be using the drag formula to find that, which is going to be negative b times v squared times v hat. And we're also going to assume that F net is equal to the sum of all forces acting on the system. For this experiment, we are going to use a point of reference, which in this case is going to be a ruler. We're going to drop an object of a known mass, which in this one, I'm going to be using a stress ball with a mass of 5 ounces or 0.14 kilograms. And using tracker, we're going to record the position of the object as it falls. Using the computer models, we're going to find the exact position of the object and with and without air resistance. The experiment, which you can see here, was just a ball dropping from about the height of a bed in a dorm room. As you can see here, the tracker data, it's not exactly a perfect curve. That could be for a variety of reasons. That could be from me misclicking. That could be from gusts of air in the room affecting the trajectory of the ball. But as you can see, it's not a perfect graph. For the computer models, you can see that we use two lines of code here. You can see that we changed the mass of the ball to start with, and we also had to change the delta t to equal 1 frame or 1/30th of a second per frame. You can see the B we used for drag, which we found that just by basically guessing. And over here you can see the code that was written to properly facilitate the drag model. And comparing the models, you can see that both computer models have nice straight curves. Um, for some reason, the simulation without drag, it started at a higher height than the other ones, even though I had it input at the same height. Not really sure what happened there, but I just know that that's improper. But you can see they all have nice smooth curves except for the experiment data. And as you can see, it's also closer to the data recorded by the simulation with drag. There are some definite errors that happened here. Tracker, the ruler I was using to calibrate tracker was at a slight angle. The camera itself was at a uh, slight angle. And if you watch the video, the ball did not drop straight down. It had an X and Z component to its motion. The computer data, as you could see in the graph, the uh, gravity simulation definitely did not even start at the right point. B is found by approximation, so that's also not going to be exact. And the data for the graph without drag has a different starting point. Which graph predicts terminal velocity? The computer graph, which also factors drag, can predict terminal velocity. It is also possible to observe terminal velocity in the real world model if it happened over a longer time, because eventually your acceleration is just going to, or your change of position is just going to become a flat line instead of an accelerator, a curve. If the ball was thrown up before it began to fall, that would not change terminal velocity, as that is a factor of drag and mass. And the starting position of the fall would change, of course, if you dropped it or if you threw it up in the air first. But other than that, nothing would change relative to this lab, as it would just be the same mass and the same surface area. And thank you for watching.